result, and in future theory used a lot. Okay. All right. Now here, the way that this, the way you generate these the product of transpositions, it's not necessarily unique. Right. That's the next point that I'll try to show you. Take this product of cycles. Okay. Now have a look. You've got here a 1, 2 and a 1, 2. So these are not disjoint, right? They're not disjoint cycles. But these two are, right? Yeah, these two are. Split this into. So the 1, 2, that's already in the form of a transposition, right? It's already of length 2, a cycle of length 2. Just leave it here. Okay. Now this you can split up, right? A1, A2, A3. So on the right hand side, so it'll be this one. It'll be A1, A2, so 4, 7, and then on the left hand side, it'll be A1, A3, so 4, 6 here on the left hand side, right hand side. Right? Now it's a bit more complicated. Now we've got 4. So the next transposition here would be A1, A4. Right? So A1, A2, A1, A3, A1, A4. So you've got 4, a cycle of length 4 now. So the right hand one will be 1, 2 there, and then 1, 3 there, and then 1, 5 there. Okay, and there's the result. You've now taken this product of cycles and split it up, in a sense, into a product of transpositions there. Okay, now I've put here 2 ways, exclamation mark. There's 2 ways we can go about doing this, and we'll get 2 different results showing that when you take a transposition and you make a product, when you take a permutation and you from it make a product of transpositions, you don't necessarily get the same result each time. You can do it. That product is not unique, put it that way. Okay. So now here's a different way of doing it. Here we just ignored the fact that these 2 cycles are not disjoint, right? And we just got that. But now let's do it a different way. So expand these out into full bracket form permutations. Right? So we're applying 3 permutations, and we expand these out this way. Full bracket form expression of your permutation, and we multiply 3 permutations. Okay, so you multiply 3 of these permutations, this one, this one, this one, and you get the result, which is just 1 permutation. Right? That's step 1. Okay, from that 1 result permutation, find its disjoint cycles. So you do something like this. Okay, do this as homework. So that's step 2. You take your 1 permutation, full bracket form permutation, and find its the product of its cycles, right? Disjoint cycles. Okay, and then find the factors. Split these in turn into a product, each one, a product of transpositions. So this one would be, what would it be? It'd be on the right, it'd be 1, 2 on the right and 1, 4 on the left. And for this one it'd be 3, 8 on the right, and then 3, is that right? No, sorry, 3, 5 on the right, and then 3, 7, and then 3, 8. Right? Right? So do that. Now, I'm giving you the results here from the text. when you do multiply these three out and then split them into a product of disjoint cycles, you'll get this. Do it for homework if you want. And then you split these into transpositions. So you'll get 2, 3, and then 2, 5, and then 4, 6. Ooh. Yeah, that's right. Yeah, 4, 7, and then 4, 6. Okay. Now look at that result, and look at this result. They're quite different. Now both of these, they're all products of transpositions, and they're the same. The effect's the same. They're the same permutation as when you work all this stuff out. But so products of transpositions. So products of transposition are not unique. Right? So like this one's quite different form from this one. Okay, now I got a little bit of board space left, so I'm giving a little bit more theory. Now, a transposition is just a very shorthanded. A transposition can be a permutation, right? It's the very special case where the permutation simply just swaps two elements, A and B, and leaves all the others unchanged. Right? It's still a permutation, but a special case. Now, so that means that a transposition is still a member of the group of S of n, symmetric group. It's still a group member, okay? And as a group member of a group, it must have an inverse, right? So what is the inverse of a transposition? So now the general form of transposition is just AB. Forget about the comma. So what is the inverse of this element? A transposition is an element of your S of n. Well, the answer is that it's just itself, right? So the inverse is equal to itself. So if you like, AB is the same as the inverse of AB. Now that you can argue, you can show that that's true algebraically, as I'll do in a moment, or just physically in common sense. I mean, what is a transposition? It's just a swapper, right? So if you swap A and B, and then you do it again, so you're now swapping the B back to the A, you end up with what you started with, right? And what you started with, that's just the unit element, E. So if you apply a transposition, the same transposition twice, you end up with the unit, okay? If you swap two objects and then swap again, you end up with what you started with, right? So the inverse of a transposition is just itself. Now here's the algebraic proof. If you do it twice, from what I just said, that's equal to E, right? Now post-multiply on both sides by the inverse. So like you get this, and E times in, well, you just get that, right? Now the exponents, 2 minus 1 is just 1, so you just get your transposition AB. But that is then equal to the inverse, right? So, summarizing, the inverse of a transposition is itself. Okay, remember that, because I've run out of board space, but the next thing I'll do is I will ask you, take a general permutation, put it into a product of transpositions. Each permutation, is a product of transpositions. So take a random permutation, express it in the form of a product of transpositions, and then I ask you to find the inverse of that permutation. Now you know how to do that for bracket form, but how do you do it for a product of transpositions? And we'll do that next, and it will use this result that the inverse of transposition is just equal to itself. Right? Okay, I'll stop there. So this is the end of the session. One whiteboard's worth of material is one session.